Right now, everything you know about the beginning of reality might be wrong. For nearly a century, we have believed the universe exploded into existence from a single point, the Big Bang. But what if that moment never actually happened? What if the universe didn't begin? It arrived. Imagine this: no explosion, no cosmic birth, just a silent, endless reality that existed long before time itself. A universe with no beginning, only transformations, cycles, and hidden eras erased from our memory. What if there were universes before ours? What if we are living inside the ashes of a cosmic event we have never truly understood? And what if the Big Bang was just one chapter in a story far older than space and time? Leave a like and subscribe to the channel if you love the content, because tonight we're going to explore the theories that scientists don't usually talk about, the strange clues, the mathematical whispers, and the possibilities that break every rule we thought we knew. If the universe did not start with the Big Bang, then the real question is, what came before everything? Get ready, we begin. There's a story that we've all been told since we were kids, a story so fundamental to our understanding of reality that most of us never stop to question whether it's actually true. It's the story of how everything began. Close your eyes for a moment and imagine this scene. Everything that exists, every single atom, every particle, every bit of matter and energy in the entire observable universe was once crushed together into a single point so small that it defies imagination. We're not talking about something the size of a grain of sand or even an atom. We're talking about a point that's essentially nothing, infinitely small, infinitely dense, containing all of reality compressed into something that shouldn't even be able to exist. This is what scientists call the singularity, and the explosive expansion from this impossible point is what we call the Big Bang. For nearly a century, this has been the foundation of modern cosmology. It's what we teach in schools, what we show in documentaries, what we present as scientific fact. The Big Bang Theory isn't just some random guess or philosophical idea that someone came up with while sitting around thinking deep thoughts. This theory emerged directly from the mathematics of Einstein's general theory of relativity in the early 20th century. When scientists like Alexander Friedmann and Georges Lemaitre took Einstein's revolutionary equations and applied them to the universe as a whole, something extraordinary happened. The math pointed backward to a single moment, a single point where everything began. Think about that for a second. These brilliant physicists weren't trying to prove any particular religious or philosophical idea. They were simply following the mathematics wherever it led them, and the mathematics led them to conclude that the universe had a definite beginning. Time itself started at that moment. Before the Big Bang, according to this view, there was no before. There was no time, no space, no matter, no energy, no nothing. The very concept of before becomes meaningless when you're talking about the beginning of time itself. But here's where things get really interesting, and this is what we're going to explore in depth today. That groundbreaking work happened over 100 years ago. Since then, our understanding of the universe has exploded in ways that those early pioneers could never have imagined. We've built telescopes that can see nearly to the edge of the observable universe. We've developed particle accelerators that can recreate conditions from fractions of a second after the supposed Big Bang. We've discovered dark matter and dark energy, mysterious substances that make up most of the universe, but that we still don't fully understand. We've detected gravitational waves rippling through space-time itself, confirming predictions that Einstein made a century ago. Our mathematical tools have become incredibly sophisticated. We can simulate the evolution of entire galaxies on supercomputers. We can calculate what happened in the first microseconds after the Big Bang with stunning precision. We've mapped the cosmic microwave background radiation, the afterglow of the Big Bang itself, with incredible detail. We've learned about cosmic inflation, a period of exponential expansion that happened in the earliest moments of the universe's history. We've discovered that the expansion of the universe is actually speeding up rather than slowing down, driven by something we call dark energy that we barely understand. So with all this new knowledge, with all these new observations, with all these refined theories and better mathematics, we have to ask ourselves a critical question. Does our modern understanding of the cosmos still require this point-like beginning? Does all the evidence still point toward the Big Bang as the absolute start of everything? Or have we discovered something that might allow us to challenge this fundamental assumption? Could it be possible that the universe didn't actually begin with the Big Bang? Could there be something that came before, some way to extend time back beyond what we thought was the absolute beginning? Now, before you start thinking this is just some wild speculation or fringe science that's trying to overturn established facts, just for the sake of being controversial, you need to understand something important. What we're about to discuss comes from serious, rigorous work by respected physicists and cosmologists who are using the same mathematical tools and the same observational evidence that led to the Big Bang theory in the first place. These aren't people making stuff up or ignoring the evidence. They're following the math and the observations wherever they lead, just like Friedman and Lemaitre did a century ago. The difference is that they're working with much more sophisticated tools and much more detailed knowledge of how the universe actually behaves. Recent developments in theoretical physics and cosmology have opened up some truly remarkable possibilities. Scientists have found potential loopholes in what we thought were airtight arguments for a cosmic beginning. They've discovered scenarios where the universe might be able to avoid having a definite starting point. They've shown that under certain specific conditions, it might be possible for time to stretch back infinitely into the past, with no moment that we can point to and say this is where it all began. These aren't just wild ideas thrown out there to generate headlines or sell books. These are serious scientific proposals that have passed peer review and have been published in respected physics journals. But to understand how we might avoid the beginning of time, to really grasp what these new ideas mean and whether they actually work, we first need to understand exactly what we mean when we talk about the beginning of the universe. We need to dig deep into the mathematics and physics that led scientists to conclude there was a Big Bang in the first place. We need to understand what a singularity really is, what it means for the universe to have a beginning, and how physicists actually go about investigating these questions. Only then can we properly evaluate whether these new ideas actually allow us to escape the Big Bang, or whether the universe really did have a definite starting point after all. Let's start by understanding what physicists mean when they talk about the beginning of the universe. The key concept here is something called a past singularity. Now, you've probably heard the word singularity before, maybe in science fiction movies or documentaries about black holes. But what does it actually mean in this context? A past singularity would be a point in the history of the universe where all of space, every single location that would eventually spread out to become galaxies and stars and planets and everything else, was literally at the same exact point. Not just very close together, not just compressed into a tiny volume, but actually and truly at the same infinitesimal location. Think about that carefully, because it's a crucial distinction. This isn't like taking all the air in a room and compressing it into a small box, where the air molecules are very close together, but still occupy different positions. A true singularity means that every point in space, every location that we now think of as being separate and distinct, was genuinely the same point. There was no separation, no distance, no here versus there. everything was literally at one location, and that location was infinitely small. From this perspective, asking what was next to this point or what was outside of it becomes meaningless. There was no next to it or outside of it because all of space was contained in that one point. When the earliest cosmologists like Alexander Friedmann in the early 1920s and Georges Lemaitre later in that decade started working with Einstein's field equations, they made an incredible discovery. Einstein had given us a completely new way of thinking about gravity, not as a force that pulls objects together, but as a curvature of space-time itself. Massive objects like stars and planets create dips and curves in the fabric of space-time, and other objects moving through that curved space-time follow paths that we perceive as gravitational attraction. It's like placing a heavy ball on a stretched rubber sheet. The ball creates a depression, and if you roll a marble nearby, it will curve toward the ball because it's following the curved surface of the sheet. Friedmann and Lemaitre asked a bold question. What do Einstein's equations tell us about the universe as a whole? Not just about individual stars or planets or solar systems, but about all of space and all of time taken together. When they solved Einstein's equations for an expanding universe, which observations were beginning to suggest was the case, they found something profound and unsettling. If you take the equations that describe an expanding universe and run them backward in time, like rewinding a movie, you find that all points in space converge on a single location. The math was absolutely clear about this. There was no escaping it within the framework they were using. According to their calculations, if you trace the expansion of the universe backward far enough, you would inevitably reach a point where the density of matter and energy became infinite, where the temperature became infinite, where the curvature of space-time itself became infinite. This point of infinite density and infinite curvature is what we call a singularity. And if the math says there's a singularity at the beginning of the universe's history, then it seems like we're forced to conclude that time itself began at that moment. There was nothing before the singularity because before doesn't make sense when you're talking about the origin of time itself. Now, here's something really important that we need to understand about those early models. Friedmann and Lemaitre were working under some very significant constraints. Remember, they were doing these calculations in the 1920s. They didn't have computers. They didn't have the vast amounts of observational data that we have today. They couldn't just plug equations into a supercomputer and let it crunch the numbers. They had to do everything by hand, using pen and paper, working through incredibly complex mathematical equations step by step. Because of these limitations, they had to make some simplifying assumptions to make the problem manageable. One of the biggest assumptions they made was that the universe is perfectly smooth and uniform everywhere. They imagined a cosmos where matter and energy are distributed with absolute evenness, like a perfectly stirred cosmic soup with no lumps, no clumps, no variations in density from one place to another. Mathematically, we describe this as a homogeneous and isotropic universe. Homogeneous means it's the same at every location, and isotropic means it looks the same in every direction you look. This assumption made the equations much simpler to solve because you could describe the entire universe with just a few numbers, instead of having to track what's happening at every single point in space separately. But there's an obvious problem with this assumption. Our universe is definitely not perfectly smooth. Look up at the night sky and you'll see the evidence immediately. We have stars, which are dense concentrations of matter with vast empty spaces between them. We have galaxies, which are collections of hundreds of billions of stars grouped together. We have clusters of galaxies, and superclusters of galaxy clusters, and vast cosmic voids where there's almost nothing at all. On the larger scales, the universe looks like a giant cosmic web, with filaments of galaxies separated by enormous empty regions. This is not a smooth, uniform distribution of matter. And this lumpiness, this structure in the universe, isn't just a minor detail that we can ignore. It's absolutely fundamental to why we exist. If the universe were truly perfectly smooth, if matter and energy were distributed with perfect uniformity, then gravity would have nothing to work with. There would be no regions that were slightly denser than others, no places where gravity could start pulling matter together to form the first stars and galaxies. Without those initial tiny fluctuations in density, the universe would have remained a perfectly uniform, boring sea of particles, gradually getting more and more dilute as it expanded. No stars would ever form. No planets would ever form. We wouldn't be here having this conversation. So this raises a really important question that cuts to the heart of what we're trying to figure out. Could the lumpiness of the universe, the fact that matter isn't perfectly uniformly distributed, actually prevent the universe from converging on a single point when we run the cosmic movie backward? The early models that predicted a singularity at the beginning assumed perfect smoothness. But we know the universe isn't perfectly smooth. So does that mean the singularity might not actually exist? Could the very imperfections and irregularities that make the universe interesting and allow us to exist also mean that there wasn't really a definite beginning to time? Keep that question in mind because it's going to become really important as we dig deeper into this mystery. But before we can answer that question, we need to talk about another crucial piece of the puzzle that completely changed how we think about the early universe. The fact that our universe is mostly smooth, even though it's not perfectly smooth, is actually kind of mysterious when you think about it carefully. Sure, we have structure on relatively small scales like galaxies and clusters of galaxies. But when you zoom out and look at the really big picture, at scales of hundreds of millions of light years or more, the universe is remarkably uniform. The temperature of the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, is almost exactly the same in every direction we look. It varies by only about 1 part in 100,000 from one region to another. This uniformity is actually a puzzle. In standard Big Bang cosmology, without any additional ingredients, regions of space that are now on opposite sides of the observable universe would never have been in contact with each other. They would never have had a chance to exchange energy and reach the same temperature. It's like having 2 pots of water on opposite sides of the Earth that somehow ended up at exactly the same temperature without ever having been connected or influenced by each other. How is that possible? Why would distant regions of the universe that could never have interacted all end up with almost exactly the same properties? To solve this problem, cosmologists introduced a new concept called cosmic inflation. This is one of the most important ideas in modern cosmology, and understanding it is crucial to understanding the debate about whether the universe had a beginning. Inflation describes a period of incredibly rapid, exponential expansion that occurred in the very first moments of the universe's history. And when I say rapid, I mean almost incomprehensibly fast. During this inflationary period, which lasted for an absurdly short amount of time, maybe something like a trillionth of a trillionth of a trillionth of a second, the universe expanded by an enormous factor. To give you some sense of the scale, imagine taking a region of space that's smaller than a single proton, one of the particles in the nucleus of an atom. Now expand that region by a factor of at least 10 to the power of 26. That means multiplying its size by 1 followed by 26 zeros. The region would grow from smaller than a proton to larger than a galaxy, or possibly much larger, all in a tiny fraction of a second. This is expansion happening faster than you can possibly imagine, faster than anything in your everyday experience could prepare you for. It's like taking a photograph and zooming in so far that a single pixel fills an entire movie screen, except the zoom happens instantaneously and the scale is billions of times more extreme. Why does this help explain the uniformity of the universe? Because inflation takes tiny patches of space that were in contact with each other in the extremely early universe, regions that had time to reach the same temperature and share properties, and it blows them up to enormous sizes. After inflation, those originally tiny patches that were in equilibrium with each other become large enough to encompass regions that are now on opposite sides of our observable universe. So, the reason distant parts of the universe all have the same temperature is because they were once part of the same tiny patch of space before inflation stretched everything out to cosmic scales. At the same time, inflation doesn't make everything perfectly smooth. Quantum mechanics tells us that at extremely small scales, there are always tiny random fluctuations in energy and density. These fluctuations are an unavoidable consequence of the uncertainty principle, one of the fundamental features of quantum mechanics. During inflation, these microscopic quantum fluctuations get stretched out along with everything else, blown up from subatomic scales to cosmic scales. These amplified quantum fluctuations become the seeds of all the structure we see in the universe today. Regions that were slightly denser than average would have stronger gravity, attracting more matter, eventually growing into galaxies and clusters of galaxies. So, inflation explains both why the universe is mostly smooth and why it has just the right amount of lumpiness to form interesting structures. Originally, cosmologists thought about inflation as a distinct phase in the history of the universe. The Big Bang happened, then immediately afterward came this brief period of inflation, and then inflation stopped and the universe transitioned to the more normal, slower expansion that we observe today. The universe inflated rapidly for a brief moment, then the inflation ended everywhere and regular physics took over. It was a neat, clean picture where inflation was just one chapter in the cosmic story. But then cosmologists realized something absolutely profound that changes everything. This inflationary expansion didn't necessarily have to stop everywhere at the same time. Think about it like this. Imagine you have a pot of boiling water on the stove. Bubbles form in different places at different times. Some bubbles rise to the surface and pop, while other regions of the water are still boiling and forming new bubbles. The boiling doesn't stop everywhere simultaneously. It's a process that continues in some regions while ending in others. Inflation might work the same way. In certain regions of space, the inflationary expansion might end, creating what we call a bubble universe. Inside these bubbles, the exponential expansion has stopped and the laws of physics operate the way we observe them in our universe. Matter can clump together to form stars and galaxies. The normal processes of cosmic evolution can proceed, but crucially, outside these bubble universes, in the space between them, there's still a greater inflating space-time that continues expanding exponentially. This inflating background doesn't stop. It keeps growing, and as it grows, new bubble universes constantly form within it, like new bubbles forming in boiling water. This scenario is called eternal inflation, and it has mind-boggling implications. If inflation is eternal into the future, if it keeps creating new bubble universes forever and ever with no end, then it seems reasonable to ask whether it could also be eternal into the past. If the inflating space-time has no end in the forward direction of time, why should it have a beginning in the backward direction? Maybe inflation has been happening forever, with no starting point, with time stretching infinitely into both the future and the past. And if that's the case, if the greater inflating space-time that contains all the bubble universes has no beginning, then maybe the universe as a whole never had a Big Bang at all. Maybe what we call the Big Bang is just the moment when our particular bubble universe formed within an eternally inflating space-time that has always existed. You can see how our picture of cosmic history has gotten dramatically more complicated over the past century. We've gone from a relatively simple story of a universe expanding from a single point to a complex scenario involving our inflationary period that might be eternal, creating an infinite number of bubble universes, each with its own history and properties. And in the middle of all this complexity is the deep question we're trying to answer. Did the universe really have a beginning? Did time start at some definite moment in the past? Or is it possible that time stretches infinitely backward with no ultimate origin? To navigate this increasingly intricate landscape and figure out whether there really was a beginning of time, we need to be very careful and systematic in how we approach the problem. We need the right mathematical tools, the right physical concepts, and the right way of thinking about space-time to explore this question rigorously. We can't just wave our hands and make philosophical arguments. We need to use the precise language of mathematics and physics to investigate what the equations actually tell us about the past history of the universe. So how do physicists tackle this problem? How do they figure out whether space-time had a beginning? The approach is surprisingly straightforward in principle, even though the details can get quite technical. Physicists start by choosing a coordinate system for space and time. A coordinate system is basically a framework that allows you to label events and locations in space-time. You can think of it like a grid overlaid on the universe that lets you specify where and when something happens using a set of numbers. Once you have this coordinate system set up, you trace those coordinates backward into the past and see what happens. You follow the paths that objects would take through space-time as you run the cosmic clock in reverse. If everything goes smoothly and you can continue tracing these paths back indefinitely, then the space-time might not have a beginning. But if at some point you reach a place where you cannot continue tracing the paths any further backward, where something about the coordinate system breaks down or becomes ill-defined, then you've potentially found a boundary to space-time. The places where this breakdown occurs are called singularities. In the context of Big Bang cosmology, there's a singularity in the past where all the different paths through space-time, all the possible histories that different particles or light rays could have followed, converge at a single point. Beyond this singularity, you cannot trace the paths any further back. The coordinates don't make sense anymore. The math breaks down. And traditionally, this singularity has been interpreted as representing the beginning of time itself, the moment before which there was literally nothing because there was no time for anything to exist in. But here's where things get subtle and really interesting. There's an important lesson we can learn from another type of singularity that you've definitely heard about before. This example will help us understand that not all singularities are created equal, and that we need to be very careful about how we interpret what a singularity actually means. This example is going to give us the conceptual tools we need to properly investigate whether the Big Bang singularity truly represents the beginning of everything or whether it might be something less absolute. That example is the black hole, one of the most fascinating objects in the entire universe. Think about a black hole for a moment. Specifically, let's consider the simplest possible type of black hole, one that's not rotating and doesn't have any electric charge. This is described mathematically by something called the Schwarzschild metric, named after Carl Schwarzschild, who figured out the solution to Einstein's equations for this situation way back in 1916, just a year after Einstein published his general theory of relativity. Schwarzschild was actually serving in the German army during World War I when he did this calculation, which makes his achievement even more remarkable. If we use Schwarzschild coordinates to trace paths from a safe distance far away from the black hole and follow them inward toward the center, we discover something really surprising. The coordinates blow up and become infinite, not in just one location, but in two distinct places. One of these infinities is exactly what you'd expect. At the very center of the black hole, at what we call the singularity, the curvature of space-time itself becomes infinite. This is a genuine physical singularity, where the structure of space and time breaks down completely. Our equations stop working. The predictions become nonsensical. This is a real, honest-to-goodness singularity that represents a boundary of space-time where the known laws of physics cease to apply. But there's also a second location where the Schwarzschild coordinates become infinite, and this one appears at a very different place. This second singularity shows up at the event horizon, the famous point of no return that surrounds every black hole. The event horizon is the boundary where the escape velocity equals the speed of light. Once you cross this boundary moving inward, you can never escape back to the outside universe. Not even light can escape from beyond the event horizon, which is why black holes appear black. At this event horizon, something very strange happens in Schwarzschild coordinates. The coordinate that we use to measure time appears to blow up and become infinite. It looks like time itself comes to a complete stop right at the event horizon. If you were watching a clock fall toward a black hole from a safe distance away, you would see the clock ticking more and more slowly as it approaches the event horizon. As it gets closer and closer to that critical boundary, the clock would appear to tick slower and slower, and right at the event horizon, it would seem to freeze completely. The hands would stop moving. Time would appear to stand still. You might be very tempted to interpret this behavior as meaning that the event horizon is an impenetrable wall, a barrier that nothing can actually cross. You might think that objects falling toward a black hole get stuck at the event horizon, unable to proceed any further. You might conclude that the event horizon represents a true boundary of space-time, similar to the singularity at the center. But if you thought any of those things, you would be completely and utterly wrong. This is one of the most common misconceptions about black holes, and understanding why it's wrong is crucial to understanding the deeper point we're trying to make here. Just because the Schwarzschild coordinates break down at the event horizon, just because they can't smoothly describe what happens there, doesn't mean that space-time actually ends at that location. The mathematical difficulties we encounter are not a property of space-time itself. They're a limitation of our choice of coordinate system, like trying to describe the entire Earth using latitude and longitude coordinates, but running into trouble at the North and South poles, where all the longitude lines converge. The poles are perfectly ordinary places on the Earth's surface. They're not holes or edges or singularities in the physical sense. They're only special because of how we've chosen to label locations on the globe. An astronaut falling into a black hole doesn't experience anything special at the event horizon. They don't bounce off it, they don't get stuck there, they don't feel any particular force or see any physical barrier. From their perspective, they pass right through the event horizon just as smoothly as passing through any other region of space. The only thing that's different is that they've crossed a one-way boundary. Once they're inside the event horizon, all their possible future paths lead toward the central singularity. They can't turn around and escape back to the outside universe. But the crossing itself is unremarkable. There's no sign saying you are now entering a black hole. There's no bump or jolt or discontinuity. It's just another location in space-time. So how do we resolve this apparent contradiction? How can something that looks like a singularity in our mathematics actually be perfectly smooth and passable in reality? The answer lies in a concept called a coordinate transformation. This is basically a mathematical trick where we change the way we label points in space-time. Instead of using Schwarzschild coordinates, which have this annoying property of breaking down at the event horizon, we can switch to a different coordinate system that doesn't have this problem. For example, there's a coordinate system called Eddington-Finkelstein coordinates that combines space and time measurements in a clever way. In these coordinates, we can trace paths continuously all the way from far outside the black hole through the event horizon and down to the central singularity. No infinities appear at the event horizon when we use these coordinates. The mathematics stays completely well-behaved and smooth. Only at the central singularity, at the very heart of the black hole, where the curvature genuinely becomes infinite, do we encounter a mathematical breakdown that persists no matter what coordinate system we choose. The event horizon is what we call a coordinate singularity. It's not a real physical singularity. It's an artifact of our mathematical description, similar to how longitude is undefined at the North Pole, not because there's anything physically special about that location, but because of how we've chosen to set up our coordinate system. A penguin standing at the South Pole doesn't experience anything weird or unusual. It's just another point on the ice. The apparent singularity in our coordinates doesn't correspond to anything special in physical reality. We say that space-time is extendable beyond the event horizon precisely because we can find a coordinate transformation that reveals the space beyond it. In fact, if we use an even more sophisticated mathematical representation called a Penrose diagram, which is a type of space-time map that compresses all of space and all of time into a finite picture while preserving the important causal structure, we reveal even more surprising features. The Penrose diagram for a Schwarzschild black hole shows not just the black hole and the external universe that we live in, but also some additional regions that represent what looks like a mirror universe on the other side of the black hole and a past white hole, which is like a black hole running backward in time. These additional regions are part of what's called the maximally extended Schwarzschild solution. They're mathematically valid parts of the space-time that satisfy Einstein's equations. In principle, we could trace light rays to these places. But here's the thing, and this is really important. These extra regions almost certainly don't exist in any real black holes that form from collapsing stars in our universe. Real black holes have a history. They form when a massive star runs out of fuel and collapses under its own gravity. The space-time structure of a real black hole is different from the idealized eternal Schwarzschild solution that includes these extra regions. The white hole and mirror universe parts of the Penrose diagram are mathematical curiosities that don't correspond to physical reality in our universe. But that doesn't change the crucial lesson we've learned here. The event horizon, despite looking like a singularity in certain coordinates, is actually a coordinate singularity that can be removed by choosing better coordinates. It doesn't represent a true boundary of space-time. You can pass through it smoothly. On the other hand, the central singularity of the black hole remains a genuine physical singularity, no matter what coordinates you use. No amount of mathematical manipulation can make it go away. No light ray can pass through the central singularity to the other side. It represents a true edge of space-time where the fabric of reality itself terminates. Now we can finally return to our original question with a much deeper understanding of what singularities mean and how to tell the difference between coordinate artifacts and genuine physical boundaries. What about the Big Bang? What about the singularity that appears at the beginning of the universe when we run the cosmic expansion backward? Is it like the event horizon, a mere coordinate singularity that might have space-time extending beyond it? Or is it like the central singularity of a black hole, a genuine physical boundary where space-time truly begins? Could the Big Bang singularity be just an artifact of how we've chosen to describe the universe mathematically, rather than representing a real beginning of time? Or is it a true edge of space-time, a moment before which there was nothing because time itself hadn't started yet? To answer these questions, to really get to the bottom of whether time had a beginning, we need another powerful tool from the mathematical toolkit of general relativity. This tool is called geodesic incompleteness, and it's going to be absolutely crucial to everything that follows. Let's talk about what a geodesic actually is. In general relativity, a geodesic is the path that an object naturally follows through curved space-time when no forces are acting on it. It's the generalization of a straight line to curved spaces. On a flat sheet of paper, the shortest distance between 2 points is a straight line. But on a curved surface, like the Earth, the shortest path between 2 points is a curved line called a great circle. If you want to fly from New York to London, the shortest route isn't a straight line on a flat map. It's a curved path that arcs northward over the Atlantic, which is a segment of a great circle on the Earth's spherical surface. In space-time, geodesics play the same role. They're the natural paths that objects follow when moving freely through the curved geometry of space-time. When you throw a baseball, its arc through the air would be a geodesic if we ignored air resistance. The path is determined purely by the curvature of space-time around Earth, which we perceive as gravity. The Earth's orbit around the Sun is also a geodesic. Earth isn't being pulled by some mysterious force. It's simply following the natural path through the space-time that's been curved by the Sun's mass. Geodesics are what you get when you let objects move freely in curved space-time without pushing or pulling on them. Light travels along a special kind of geodesic called a null geodesic. This type of path has a remarkable property. From the perspective of a photon, if photons could have perspectives, no time elapses during its journey. A photon that travels from a distant galaxy to your eye, covering billions of light years, experiences zero passage of time. This is one of the strange consequences of special relativity. As you move faster and faster, time dilation causes time to pass more slowly for you, relative to stationary observers. At the speed of light, time dilation becomes infinite. Time stops completely. Null geodesics represent the paths followed by light rays through space-time, and they play a crucial role in understanding the causal structure of the universe because they represent the boundaries of what can influence what. Now, here's the key point. Geodesics, whether they're time-like paths followed by massive objects or null paths followed by light, are normally thought of as continuing forever into both the past and the future. You can extend these paths infinitely far in either time direction. A particle might actually follow a particular geodesic for only a brief period. Maybe a baseball follows its arc for a few seconds before hitting the ground. But mathematically, we can extend that geodesic infinitely far into the past and infinitely far into the future. The geodesic itself is an eternal mathematical object that exists throughout all of space-time. But sometimes, in certain space-time geometries, a geodesic reaches a point where it simply cannot be extended any further in one direction or another. These geodesics hit a dead end, a place beyond which you cannot trace them. These endpoints are called points of geodesic incompleteness, and they have a very specific interpretation in general relativity. They represent genuine boundaries of space-time, edges of the cosmic map, where reality itself ends. It's like traveling across the ocean during the age when people thought the Earth was flat. You might reach the edge of the world, where the ocean simply stops and there's nothing beyond. That's what geodesic incompleteness represents in space-time, an actual boundary where you can't go any further because space-time itself terminates. The singularity at the center of a black hole is a perfect example of geodesic incompleteness. If you follow the world line of an astronaut falling into a black hole, their path through space-time reaches the central singularity and stops. You cannot extend their world line any further into the future. Their future literally ends at that point. The equations can't tell you what happens next because there is no next. Time itself comes to an end for them at the singularity. This concept was famously used by the physicist Roger Penrose to prove that black holes must contain genuine physical singularities. His black hole singularity theorem, published in the 1960s, was groundbreaking work that eventually earned him the Nobel Prize in Physics in 2020. Using purely mathematical reasoning about how geodesics behave in space-time curved by massive objects, Penrose showed that under very general conditions, black holes must contain regions of geodesic incompleteness. You don't need to make specific assumptions about the exact form of matter or energy involved. The conclusion follows from very general principles about how gravity works in general relativity. Black holes must have true singularities where space-time ends. This was a major achievement in theoretical physics because it showed that singularities aren't just artifacts of simplified models or special cases. They're genuine, unavoidable features of general relativity under realistic conditions. Now, geodesic incompleteness by itself is pretty strong evidence for a genuine boundary of space-time. But scientists are careful people who like to have multiple independent lines of evidence, all pointing to the same conclusion before they're completely convinced of something. We're always a little worried that maybe we've made some subtle mistake, that maybe we're using the wrong coordinate system, that maybe what looks like geodesic incompleteness is actually just a coordinate singularity like the event horizon of a black hole. How can we be absolutely sure we're not being fooled? This is where another test comes in. Another hallmark of a genuine physical singularity, one that's independent of what coordinate system you happen to be using, is that the curvature of space-time blows up and becomes infinite at that location. The curvature of space-time is a measure of how strongly gravity is warping the geometry of space and time. In flat, empty space far from any massive objects, the curvature is zero. Near a star or planet, the curvature is small but measurable. Near a neutron star, the curvature is much larger. And at a singularity, the curvature becomes infinite. The beautiful thing about curvature is that it can be defined in a coordinate-independent way. There are mathematical quantities derived from something called the Riemann curvature tensor that measure how much space-time is curved. And these quantities have the same value regardless of what coordinate system you use to calculate them. If we find that these coordinate-independent measures of curvature become infinite at a certain location, we can be virtually certain that we've found a real physical singularity. It's not just a trick of our mathematical description, it's a genuine feature of space-time. At the center of a black hole, both conditions are satisfied. Geodesics terminate there, exhibiting geodesic incompleteness, and the curvature, measured in any coordinate system, becomes infinite. You can use Schwarzschild coordinates, you can use Eddington-Finkelstein coordinates, you can use any coordinate system you want, and you'll always find that the curvature blows up at the center. The combination of these two features provides extremely strong evidence for a real physical boundary to space-time at the heart of every black hole. Armed with these sharper tools and more sophisticated concepts, we can finally tackle the big question head-on. Let's use these methods to investigate whether the Big Bang represents a true beginning of time, or whether it might be something else entirely, something less absolute and more subtle than the definite start of everything that we've been taught to believe in. So what happens when we apply the test of geodesic incompleteness to the universe as a whole? What do we find when we trace all possible paths through space-time backward into the past? Well, the answer that emerges from standard cosmological models seems to confirm that the universe did indeed have a beginning. Every geodesic, every possible world line through space-time, from the path of Earth around the Sun to the trajectory of a photon traveling across the cosmos, can be traced backward in time, and they all converge on the same point in the past. Think about what this means. Take any object in the universe, any particle, any point in space. Trace its history backward through time. Now take a different object in a completely different part of the universe and trace its history backward as well. According to standard Big Bang cosmology, both of these paths, and indeed all such paths, wind up at the same infinitesimal point in the past. There's nowhere else for them to go. Every backward extended geodesic terminates at the same location, strongly suggesting that space-time itself began at that point. All roads lead to Rome, and in this case, all paths through space-time lead back to the Big Bang. And here's something that might surprise you. This conclusion about past geodesic incompleteness remains true even when you include cosmic inflation in your model. Remember eternal inflation, that scenario where the inflationary expansion continues forever into the future, constantly creating new bubble universes for all eternity? You might think that if inflation goes on forever into the future, it should also extend forever into the past, but the mathematics tells us otherwise. Even in models of eternal inflation, when you trace geodesics backward, they still converge to a beginning. This seems counterintuitive at first. If the inflating spacetime has no end in the forward direction of time, why should it have a beginning in the backward direction? Why isn't time symmetric, stretching infinitely in both directions? But general relativity isn't time symmetric in this way. The expansion of space has a direction, and when you carefully trace geodesics through an expanding spacetime, you find that they cannot be extended infinitely far into the past, even if the expansion continues infinitely far into the future. Now, demonstrating this past geodesic incompleteness rigorously usually requires making certain assumptions about the physical properties of matter and energy in the universe. Many of the classic proofs that the universe had a beginning rely on something called energy conditions. These are additional constraints that we add to Einstein's equations to ensure that matter and energy behave in physically reasonable ways. For example, one commonly used assumption is the weak energy condition. This essentially says that you cannot have negative mass densities anywhere in the universe. Negative mass would be truly bizarre. An object with negative mass would fall upward instead of downward in a gravitational field. It would accelerate away from normal matter. We've never observed anything like this, and it would violate a lot of basic physical intuitions about how the world works. The weak energy condition codifies this by ruling out negative mass densities as unphysical. Another similar condition is the strong energy condition, which says that gravity must always be attractive rather than repulsive for normal forms of matter and energy. These energy conditions help ensure that general relativity behaves in sensible, predictable ways. They prevent mathematical solutions that might satisfy Einstein's equations technically, but which don't correspond to anything that could exist in the real world. But here's the problem with relying on energy conditions to prove that the universe had a beginning. We're talking about conditions near the supposed Big Bang singularity, where energy densities become enormous, where temperatures exceed anything we can imagine or recreate in laboratories, where quantum effects become dominant, where the fabric of space-time itself might be breaking down. Can we really be confident that our usual assumptions about energy conditions still hold in such extreme circumstances? It would be much better much more convincing if we could prove that the universe had a beginning without having to assume specific energy conditions. We'd prefer an argument that relies on more minimal, more robust assumptions that we can be confident remain valid even in the extreme environment near a cosmic singularity. And this is where some important recent theoretical work comes in, work that has both strengthened the case for a cosmic beginning and simultaneously revealed some potential loopholes. In 2003, three prominent physicists named Arvind Borda, Alan Guth, and Alexander Vilenkin published a remarkable paper that significantly advanced our understanding of this question. They constructed a stronger, more general argument for past geodesic incompleteness that didn't require assuming any particular energy condition at all. Instead of making assumptions about what kinds of matter and energy could exist, they only needed to assume one thing about the expansion history of the universe. That single assumption was that the average expansion rate has always been positive throughout cosmic history. Let me be clear about what this means. They assumed that on average, over the entire history of the universe, space has always been growing larger rather than contracting. The size of the universe might increase at different rates at different times. During inflation, it increased exponentially fast. At other times, the expansion might have been slower. But averaged over cosmic history, the universe has always been getting bigger, never shrinking. This is a much weaker and more defensible assumption than specific energy conditions. We directly observe that the universe is expanding today. All the evidence from distant galaxies, from the cosmic microwave background, from our best cosmological models, tells us that space has been expanding for billions of years. The assumption is simply that this average expansion has never reversed into a net contraction. Under just this single, relatively modest assumption, Borda, Guth, and Vilenkin proved what's now known as the BGV theorem. The BGV theorem states that any universe that has, on average, been expanding throughout its history cannot have been expanding forever. It must have a boundary in the past, a point beyond which you cannot trace geodesics further backward in time. The universe cannot be infinitely old if it's been expanding on average. Time must have had a beginning. There must have been a first moment, a point where the cosmic clock started ticking. This was a really big deal in cosmology. The BGV theorem seemed to close off one of the main potential loopholes for avoiding a cosmic beginning. You might have hoped that eternal inflation, with its endless creation of bubble universes, could extend infinitely far into the past. But the BGV theorem says no. Even eternally inflating universes that will continue expanding and spawning new bubbles forever, must have started at some finite point in the past. The theorem doesn't just apply to our particular bubble universe. It applies to the entire inflating space-time that contains all bubble universes. Everything must trace back to a past boundary. For many physicists, this appeared to be a death knell for models of an eternal, beginningless universe. If even eternal inflation can't avoid having a beginning, what could? The BGV theorem seemed to provide an ironclad argument that time itself must have started at some finite moment in the past. The universe, in some form, must have had a first moment of existence. But now we need to ask the crucial follow-up question. We have strong evidence from geodesic incompleteness, reinforced by the powerful BGV theorem, that the universe has a boundary in the past. But can we be absolutely certain that this past boundary is really an end to space-time, really a beginning where time itself emerged? What if space-time is actually extendable beyond this apparent boundary, similar to how space-time extended beyond the black hole event horizon, even though the Schwarzschild coordinates made it look like an impenetrable wall? Remember our lesson from black holes. The event horizon appeared to be a singularity in certain coordinates, but it turned out to be crossable with more space-time beyond it. Could the same be true for the cosmic past boundary? Could what looked like the beginning of time in our current mathematical description actually be just a coordinate singularity, with space-time extending further back beyond it? To answer this absolutely critical question, we need to apply the other test we used for black holes. We need to check whether the curvature of space-time becomes infinite at this past boundary. If we find that curvature blows up, if there's a genuine curvature singularity, then the universe must contain a physical singularity in its past. That would represent a real beginning where space-time emerged from nothing, or from whatever preceded classical space-time. The equations of general relativity would break down there, and we'd need something beyond general relativity, probably a theory of quantum gravity, to understand what happened. On the other hand, if the past boundary doesn't contain a curvature singularity, if the curvature remains finite there, this doesn't automatically guarantee that we can extend space-time beyond it. But it opens the door to that possibility. It means we need to investigate more carefully to determine the true nature of this boundary. A finite curvature boundary might be extendable, might have space-time continuing beyond it, might not represent a true beginning of time after all. This is precisely the question that three researchers named Ghazal Geshnizjani, Eric Ling, and Jérôme Quintin set out to investigate in detail in their paper published in 2024. They took on the challenge of applying careful curvature tests to the boundaries of different possible universes. What kind of mathematical behavior does the curvature exhibit as we approach the past boundary in various cosmological models? Does it blow up catastrophically, indicating a genuine singularity? Or does it remain well-behaved, suggesting the boundary might be crossable? The answer, they discovered, depends critically on the specific expansion history of the particular universe you're examining. Different types of cosmic histories lead to different conclusions about the nature of the past boundary. This is where things start to get really interesting, because it turns out that not all universes are created equal when it comes to the question of whether they had a beginning. Remember that the BGV theorem tells us that universes which have, on average, only expanded over their entire history must have a boundary in the past. There's no escaping that conclusion if the assumptions of the theorem hold. But what Geshnizjani, Ling, and Quintin found was that universes with different types of expansion histories, ones that don't satisfy the specific assumptions of the BGV theorem, don't necessarily have to begin with a true singularity. These alternative expansion histories might potentially allow space-time to extend infinitely far into the past without encountering a real beginning. For example, imagine a universe that underwent a bounce. In this scenario, the universe was once contracting, getting smaller and denser, but then at some minimum size, it bounced and began expanding instead. The contraction phase transitions into an expansion phase without passing through a singularity. Or consider a universe that spent a long period in a static phase where the size of the universe remained constant, neither expanding nor contracting, and then later transitioned into an expanding phase like the one we observe today. These alternative expansion histories with bounces or static phases can potentially avoid past singularities according to the analysis in this new study. The spacetime might be extendable through what appears to be a boundary. The apparent beginning might be more like the black hole event horizon, a coordinate artifact that doesn't represent a true edge of reality. Time could potentially extend back beyond what looks like the Big Bang. But, and this is a really important but, there's a significant catch here. These alternative expansion histories that avoid singularities also seem to require violating the energy conditions of general relativity that we discussed earlier. Remember the weak energy condition that says you can't have negative mass? These bounce or static to expanding scenarios typically need exotic forms of matter or energy that violate such conditions. They might require something with negative pressure or other unusual gravitational properties. They might need quantum effects to behave in specific ways that we're not certain are actually possible. They might demand forms of matter and energy that we've never observed and aren't sure can exist in nature. So we're caught in a kind of trap. If you want to avoid a past singularity by having a bounce or a static phase before the expansion, you need to invoke exotic physics that violates energy conditions. And if those energy conditions are violated, it raises serious questions about whether these models describe something that could actually occur in our universe, or whether they're just mathematical possibilities that don't correspond to physical reality. This tension between avoiding a beginning and maintaining physically reasonable energy conditions isn't really an entirely new discovery. It's more a confirmation and refinement of something that cosmologists have suspected for a while. You need to break some standard assumption of general relativity, some normally satisfied condition or property, if you want to avoid having a beginning to the universe. If you play by the standard rules, if you assume that matter and energy behave in the normal ways we observe them behaving, and if you assume the universe has been expanding on average, then the equations point inexorably toward a beginning. The new study by Geshnizjani, Ling, and Quintin mostly agrees with and reinforces the conclusions of the BGV theorem. Universes that have only been expanding do have a beginning. That conclusion remains solid and well supported. But here's where things take a truly fascinating turn. In their comprehensive analysis of different cosmological scenarios, the researchers found one unusual case, one specific situation where the BGV theorem might actually be challenged, or at least where its interpretation becomes more subtle and ambiguous. This case involves some intricate mathematical properties of exponentially expanding spacetimes, and it opens up a genuinely intriguing possibility for how we might think about the beginning of the universe differently. Let's think carefully about what exponential expansion means. An inflating universe, whether we're talking about the inflationary epoch in the very early universe or the accelerated expansion driven by dark energy that we observe today, undergoes exponential growth. The size of the universe multiplies by the same factor during each equal interval of time. This is fundamentally different from linear growth, where you add the same amount each time. With exponential growth, the rate of growth itself increases over time. The universe expands faster and faster as time goes on. Now, a pure exponential function, one without any vertical shift or offset, has a mathematically interesting property. If you graph it, the function shoots upward toward infinity in the positive direction, growing without bound as time advances. But in the negative direction, toward the past, the function approaches zero asymptotically. It gets closer and closer to zero, but never quite reaches it. The curve plateaus near zero without ever touching it. Mathematically, the function extends infinitely far into the past, always staying slightly above zero, but never reaching zero itself. The BGV theorem tells us that even this eternally exponentially expanding universe should have geodesic incompleteness in the past. There should be some past boundary that geodesics cannot be traced beyond. We're naturally tempted to identify this boundary as the beginning, the moment where time started. On a space-time diagram, particularly on a Penrose diagram, which compresses infinite space-time into a finite picture while preserving causal relationships, this past boundary can be depicted as a diagonal edge at the bottom of the diagram. This represents the past boundary of the universe if there's no way to extend geodesics beyond it going backward in time. If light rays, following their null geodesics, cannot be traced past this boundary, then according to standard interpretation we should view the boundary as representing the beginning of space-time. It's an edge where reality emerged, a boundary between existence and non-existence. But the remarkable discovery made by Geshnizjani, Ling and Quintin is that there might actually be a way to extend geodesics beyond this apparent past boundary in certain specific circumstances. Our universe is well described by something with the impressive name of the Friedmann-Lemaitre-Robertson-Walker metric, which cosmologists mercifully abbreviate as FLRRW. This is the mathematical description of a perfectly homogeneous and isotropic expanding universe that we discussed earlier. It's the solution to Einstein's equations that applies when you assume the universe is the same everywhere and looks the same in all directions, with no preferred locations or orientations. It's the bread and butter of cosmology, the metric that underlies almost all our models of the large-scale universe. Now, if you add exponential expansion to the FLRW universe, something interesting happens mathematically. The FLRW metric with exponential expansion can be viewed as a special subset, a particular patch, of something called de Sitter space. De Sitter space is a solution to Einstein's equations that describes a universe containing nothing but a positive cosmological constant, which represents a constant energy density pervading all of space. It's the maximally symmetric universe with positive curvature and exponential expansion, and it's one of the most elegant solutions in all of general relativity. What these researchers showed is that it's mathematically possible to think of our observable universe, our FLRW patch with all its galaxies and structure, as just a portion of a larger de Sitter spacetime. The mathematics allows for this embedding, this way of viewing our universe as carved out from a bigger underlying structure. The FLRW cosmology we observe might be just one patch, one region, within a grander de Sitter space that extends beyond what we can see. Now, the technical details of exactly how this works involve some fairly advanced mathematics that would take us deep into the weeds of differential geometry and general relativity. But the essence of the idea, the core insight, is this. The BGV theorem insists that our universe has a past boundary based on geodesic incompleteness. If there's no way to smoothly extend null geodesics across that boundary, then we're supposed to interpret the boundary as a true beginning of time, an edge of space-time that marks the start of everything. But this new analysis shows that there may actually be a place for those null geodesics to continue to, or more precisely, a place they might have come from. The larger de Sitter space that mathematically encompasses our FLRW universe could provide a region where those geodesics extend. If our universe is extendable in this way, if the larger de Sitter space is not merely a mathematical artifact but represents actual space-time, then the apparent past boundary of our universe might be just a coordinate singularity rather than a real physical one with infinite curvature. It would be analogous to the black hole event horizon, an apparent boundary that vanishes when you adopt the right mathematical perspective. Now, we absolutely must be very careful here and avoid getting carried away with excitement about this possibility. This extended space-time beyond our past boundary may very well be, and probably is, as physically irrelevant as the white hole and mirror universe regions that appear in the maximally extended Penrose diagram of a Schwarzschild black hole. Those additional regions in the black hole Penrose diagram are mathematically valid. They satisfy Einstein's equations. You can trace light rays to them on paper, but they don't correspond to anything real in actual black holes that form from collapsing stars in our universe. Real black holes have a history. They form when massive stars exhaust their nuclear fuel and collapse catastrophically under their own gravity. The space-time structure of a real astrophysical black hole is fundamentally different from the idealized eternal Schwarzschild solution that exists unchanging for all time. The white hole and mirror universe portions of the Penrose diagram are mathematical curiosities that don't connect to physical reality. Similarly, the extended de Sitter space beyond our universe's past boundary might be a mathematical possibility that has no connection to the actual physical cosmos we inhabit. But here's what genuinely is intriguing and important about this result. We have here at least one case, one specific mathematical framework, where it's not immediately and obviously clear that the universe necessarily runs into a non-traversable curvature singularity when we trace it backward. There's at least one scenario where the question of whether space-time extends beyond the apparent past boundary becomes subtle, ambiguous, open to further investigation and debate. It's not a slam dunk, open and shut case for a definite beginning. There's wiggle room, uncertainty, a possibility that perhaps time doesn't have an absolute starting point after all, at least in this one special scenario. However, and this is crucial, the real universe throws a major wrench into this elegant mathematical possibility. For this extension to actually work, for our patch of FLRW universe to smoothly transition into the surrounding de Sitter space, very specific and stringent conditions must be satisfied. The transition has to be smooth and continuous, with no abrupt jumps or discontinuities in the geometry of space-time. You can't have sudden changes in curvature or energy density at the boundary. Everything has to match up perfectly. The only way for this smooth transition to occur is if the exponentially accelerating component that drives the expansion, what we often describe as the cosmological constant or dark energy, completely and utterly dominates over any density fluctuations at the supposed beginning of our universe. The cosmological constant would need to be so overwhelmingly dominant, so much stronger than anything else, that any variations in energy density, any lumpiness or irregularities in the distribution of matter and energy would be absolutely negligible by comparison. If the density fluctuations are incredibly tiny, approaching zero, then yes, space-time might be smoothly extendable past the past boundary of our universe. We might not have a physical past singularity after all. The apparent beginning might be just a coordinate effect, and time could extend back beyond it into the larger de Sitter space. But if there are significant density fluctuations, if there's meaningful lumpiness in the distribution of matter and energy near the boundary, then those fluctuations would actually close off the possibility of extension. They would create inhomogeneities and irregularities in the geometry that would prevent the smooth matching to de Sitter space. Instead of a smooth coordinate boundary that we can mathematically cross, those density fluctuations would transform the boundary into a hard curvature singularity, a genuine physical edge where the curvature of space-time blows up and becomes infinite. That would eliminate any possibility of space-time existing beyond it. We'd be back to having a real, true beginning of time with nothing before it. And here's the absolute kicker, the fatal flaw in this scenario when applied to our actual universe. Our universe most definitely, absolutely, certainly had density fluctuations at very early times. We know this beyond any shadow of doubt because if the universe had been perfectly smooth, if there had been no variations in density whatsoever, then there would be no galaxies today. There would be no stars, no planets, no solar systems, no us. The universe would have remained a boring, uniform sea of particles spreading out and thinning forever, with no interesting structures ever forming. We can actually see the evidence for these early density fluctuations in the cosmic microwave background radiation. This is the afterglow of the Big Bang, light that was emitted when the universe was only about 380,000 years old. When we map this radiation across the entire sky, we see tiny temperature variations, small fluctuations that represent regions that were slightly denser or slightly less dense than average. These fluctuations are only about 1 part in 100,000, extremely small, but they're absolutely crucial. Those tiny seed fluctuations were amplified over billions of years by gravitational instability. Regions that were slightly denser had slightly stronger gravity, which attracted more matter, making them even denser, which increased their gravity even more, in a feedback process that eventually produced galaxies, galaxy clusters, and all the large-scale structure we observe today. Without those initial fluctuations visible in the cosmic microwave background, none of the interesting features of our universe would exist. So the very density fluctuations that are necessary for our existence, the very imperfections and irregularities that make the universe interesting and allow structure to form and permit life to arise, are also precisely the things that would prevent the smooth extension through the past boundary. It's a wonderfully ironic situation. The same lumpiness in the early universe that allows galaxies and stars and planets and us to exist is also what enforces a hard boundary, a true beginning to time. And here's another layer of irony that makes this even more interesting from a historical perspective. Remember how Friedman and Lemaitre, when they first derived the Big Bang model, had to assume the universe was perfectly smooth? They glossed over any density fluctuations, treating the universe as completely homogeneous and isotropic because that was the only way they could solve the equations with the tools available to them. Their simplified model predicted a singularity at the beginning, a true start to time. Now we're finding out that the density fluctuations they neglected, the deviations from perfect smoothness that we now know must exist, might actually make it more likely that their conclusion was correct. The imperfections they ignored for mathematical convenience turn out to reinforce rather than undermine the idea of a genuine beginning. The real universe, with all its lumpiness and structure, probably does have a true past singularity, whereas a hypothetical, perfectly smooth universe might have been able to avoid one. Reality is stranger and more interesting than the simplified models. So where does all of this leave us? What can we actually conclude about whether the universe had a beginning? What's the bottom line after all this complex physics and mathematics? Well, based on our current understanding, the preponderance of evidence still suggests that yes, there probably was a genuine beginning of time. The hope that eternal inflation could somehow stretch infinitely far into the past, avoiding any beginning, appears to be blocked by the BGV theorem. That theorem remains robust and well supported. The possibility of avoiding a beginning through a smooth extension into der Sitter space seems to be prevented by the density fluctuations that we know with certainty existed in the early universe. Those fluctuations, which we can literally see in the cosmic microwave background radiation, would create the kind of inhomogeneities that turn a smooth coordinate boundary into a hard curvature singularity. Almost every avenue we examine for avoiding a cosmic beginning seems to run into significant obstacles, either mathematical, physical, or observational. But we need to be humble and recognize that the true final answer to this profound question is buried deep in areas of physics that we don't yet fully understand. The complete resolution awaits discoveries that haven't been made yet. Much depends on the detailed physics of cosmic inflation, and we don't have a complete theory of inflation. We don't know with certainty what field or mechanism drove the inflationary expansion. We don't know exactly how inflation started or precisely how it ended. Different models of inflation make different predictions and have different implications for the past boundary of space-time. Some of these questions may not even be answerable through observations because the relevant physics occurred at energy scales and time scales that are far beyond what we can directly probe with telescopes or experiments. The very earliest moments of the universe, the times closest to the supposed beginning, involve energies that are trillions of times higher than what we can achieve in the most powerful particle accelerators. We may never be able to directly test what happened then. Moreover, the final definitive answer to whether time had a beginning almost certainly awaits our development of a successful theory of quantum gravity. This would be a framework that successfully unifies general relativity, our best theory of gravity and space-time, with quantum mechanics, our best theory of the microscopic world of atoms and particles. Right now, these two pillars of modern physics are fundamentally incompatible with each other in certain regimes. Quantum mechanics says that everything is inherently uncertain and probabilistic at small scales. General relativity treats space-time as a smooth, continuous fabric that can be described with precision. When you try to apply both theories simultaneously in situations where both should matter, such as near the supposed Big Bang singularity, where the entire universe was compressed to subatomic scales, the theories give nonsensical, contradictory results. The equations blow up and produce infinities that have no physical meaning. This tells us that we're missing something fundamental, that neither theory alone is adequate to describe what really happens in such extreme conditions. Even if the classical equations of general relativity suggest that the universe approaches a point of infinite density in the past, our current understanding of physics absolutely and completely breaks down before we actually reach that point. When the universe was incredibly tiny and dense, quantum effects would have been enormously important, perhaps even dominant over classical gravitational effects. We simply cannot trust purely classical general relativity in that regime. It's like trying to use Newtonian physics to describe objects moving near the speed of light. The theory just isn't designed to handle that situation. Quantum mechanics might smooth out the classical singularity in ways we can't yet calculate. It might prevent the density from ever becoming truly infinite. The inherent uncertainty in quantum fluctuations might put a floor on how small and dense things can get. Or quantum gravity might give us a quantum bounce scenario where the universe transitions smoothly from a contracting phase to an expanding one without passing through a singularity. The contraction might reach some minimum size determined by quantum effects, then reverse into expansion, with no true beginning or end to time. Alternatively, quantum gravity might tell us that the entire question of what happened at time equals zero is fundamentally meaningless. Time itself might emerge from some more fundamental quantum structure. In some approaches to quantum gravity, like certain versions of loop quantum gravity or causal set theory, time isn't a basic ingredient of reality, but rather an emergent property that appears only in certain limits or regimes. In such theories, asking what came before the Big Bang might be like asking what's north of the North Pole. It's not that we don't know the answer, it's that the question itself doesn't make sense. You can't go north from the North Pole because you're already at the northernmost point. All directions from there are south. The honest truth is that we simply don't know. We don't yet have the theoretical tools to definitively answer these deepest questions about cosmic origins. The physics of the very early universe, particularly the physics at or near the supposed initial singularity, involves regimes where our current theories demonstrably break down. Until we have a working theory of quantum gravity that's been tested and verified, we're essentially working with incomplete information. We're trying to solve a puzzle while knowing that some of the most important pieces are still missing. But here's what I find absolutely stunning and incredible about all of this research, and in a way it's even more remarkable than any specific answer about whether the universe had a beginning. The most mind-blowing aspect of this entire line of inquiry isn't whether we conclude yes, there was a beginning, or no, time is eternal. What's truly extraordinary is the simple fact that we can even hope to meaningfully address questions like this in the first place. Think about what we're attempting to do here. We're trying to determine the ultimate origin of everything that exists. We're investigating whether time itself had a beginning, whether there was a first moment in the history of reality, whether the universe emerged from nothing or has existed eternally. These are questions that for most of human history would have been considered purely philosophical or theological, forever beyond the reach of scientific inquiry. They're questions about the most extreme conditions conceivable, involving energies billions of times beyond anything we can create in our laboratories, describing events that occurred billions of years before Earth existed, analyzing processes happening at scales trillions of times smaller than atoms. And yet, through pure thought, through mathematical reasoning, through careful observations of the universe as it exists today, and clever inference about the past, we've made genuine, substantive progress on these questions. We're not just wildly speculating or making things up. We have rigorous mathematical tools like the BGV theorem that place concrete constraints on the past history of the universe. We have observations of the cosmic microwave background that tell us about conditions and fluctuations in the very early universe. We have general relativity that allows us to extrapolate backward in time with substantial confidence. We can meaningfully discuss sophisticated concepts like geodesic incompleteness, curvature singularities, coordinate transformations, and space-time extensions. We're doing real science on the origin of the universe itself. We're making testable predictions. We're ruling out entire classes of models based on observations. We're narrowing down the possibilities through a combination of theory and experiment. The fact that this is even possible is perhaps the most astounding thing of all. A human being, a collection of atoms that came together relatively recently on a small rocky planet orbiting an ordinary star in an unremarkable galaxy, can contemplate the beginning of all space and time and have something meaningful and true to say about it. That fact alone might be more extraordinary than any specific answer we eventually discover. The fact that the universe is comprehensible to us at all is deeply remarkable. The fact that the same mathematical laws that describe falling apples and planetary orbits also accurately describe the evolution of the entire cosmos across billions of years is stunning. The fact that we can trace our cosmic history back to tiny fractions of a second after the apparent beginning and have our theoretical models match observations with incredible precision is extraordinary. The fact that we can even conceive of tools like the BGV theorem or understand the subtle difference between coordinate singularities and physical singularities shows how far human understanding has progressed. Of course, we're not done. We may never be completely done. There may always be deeper questions waiting to be asked, more fundamental layers of reality to uncover, new phenomena that force us to revise and refine our understanding. The entire history of physics is filled with conclusions that seemed ironclad and definitive, but later turned out to be incomplete or wrong in certain regimes when new evidence emerged or new theoretical frameworks were developed. Newtonian gravity seemed like the final complete word on gravitation, until Einstein showed it was merely an approximation that breaks down in strong gravitational fields or at high velocities. Classical physics seemed to be a complete description of reality until quantum mechanics revealed an entirely new layer of reality operating at atomic and subatomic scales. Even Einstein's general relativity, as successful as it's been, must break down in certain extreme conditions where quantum effects become important. So we should hold our current conclusions tentatively, with appropriate intellectual humility. ready to revise them as new evidence and new theories emerge. The history of science teaches us to be confident in our methods while remaining open to the possibility that our current understanding is incomplete. But that doesn't mean our present understanding is worthless or that all possible answers are equally valid. We've made genuine, measurable progress. We know vastly more about cosmic origins today than we did a century ago. The question of whether time had a beginning has transformed from pure philosophical speculation into something we can address with mathematical precision and observational constraints. And regardless of what the ultimate answer turns out to be, whether the universe had a definite beginning or whether time extends infinitely into the past, in some way we don't yet fully understand, the journey to find out has been absolutely extraordinary. We've developed powerful mathematical tools and techniques. We've discovered unexpected features of the universe like cosmic inflation and dark energy. We've learned to think carefully and precisely about what singularities really mean. We've pushed the boundaries of human knowledge right to the very edge of everything, to the limits of space and time themselves. Perhaps the most important lesson from all of this is the combination of epistemic humility with confidence in our methods. We should be humble because we're clearly working at the absolute limits of our current understanding, in regimes where our theories might break down, asking questions about conditions we can never directly observe or recreate. We're dealing with the deepest mysteries of existence using tools that we know are incomplete. But we should also be confident because our scientific methods have proven remarkably, almost unreasonably successful. General relativity has passed every experimental test we've thrown at it over more than a century. The predictions of the Big Bang model, from the cosmic microwave background to the abundance of light elements, have been confirmed with stunning precision. The universe has consistently rewarded our attempts to understand it with comprehensible, beautiful answers. The question of cosmic origins truly sits at a fascinating intersection of physics, philosophy, and mathematics. It requires the full power of human reasoning, creativity, and observational ingenuity. It demands that we think extremely carefully about what we mean by fundamental words like beginning, singularity, and time. It forces us to confront the limits of our conceptual frameworks and consider possibilities that seem bizarre, counterintuitive, or even paradoxical to our everyday intuitions. But that's precisely what makes it so fascinating and compelling. That's what makes cosmology one of the most exciting fields in all of science. We're not studying some obscure, specialized corner of nature. We're investigating the biggest, most fundamental questions imaginable. Where did everything come from? Has the universe always existed? What is the true nature of time? How did something come from nothing, if indeed it did? These questions touch on the deepest wellsprings of human curiosity and our profound desire to understand our place in the vast cosmos. Every few years, new theoretical work like the Geshe-Nisjani-Lin-Quintin paper we discussed adds nuance and subtlety to our understanding. Each study reveals new possibilities or closes off previously viable options. Every new observation, from ever more precise measurements of the cosmic microwave background to detections of gravitational waves to massive galaxy surveys mapping the large-scale structure of the universe, provides new constraints on our models and new tests of our theories. Slowly, incrementally, through the collective effort of thousands of brilliant scientists working over many decades, we're assembling an increasingly coherent and detailed picture of cosmic history. And who knows what the next major breakthrough will reveal? Perhaps the development of a successful theory of quantum gravity will completely transform how we think about the beginning of the universe. Perhaps string theory, or loop quantum gravity, or some yet undiscovered theoretical framework will show that the classical singularity predicted by general relativity is replaced by something radically different at the Planck scale, the unimaginably tiny distance scale where quantum gravitational effects become dominant. Perhaps future observations of gravitational waves from the very early universe, or new probes of the cosmic microwave background, will reveal phenomena that force us to reconsider our models of inflation or the expansion history of the cosmos. But whatever we discover in the future, however our understanding continues to evolve and deepen, the fundamental fact remains that we're engaged in one of the most profound intellectual projects in all of human history. We're attempting to understand the origin of absolutely everything, and we're making real, measurable progress toward that seemingly impossible goal. We have mathematical theorems that rigorously constrain what's possible. We have observations that rule out entire categories of models. We have a conceptual and theoretical framework that allows us to think clearly and precisely about these questions even when we don't yet have all the final answers. So whether or not the universe had a beginning in the strictest, most absolute sense, whether the Big Bang singularity represents a true start to time or just an apparent boundary where our current physics breaks down and something new takes over, we should be amazed and inspired that we can meaningfully investigate this question at all. The fact that a species that evolved to hunt and gather on African savannas, whose brains were shaped by natural selection to help us survive and reproduce in a specific terrestrial environment, can now discuss geodesic incompleteness and de Sitter space and quantum gravity and the ultimate origin of the universe is perhaps the most remarkable and unexpected phenomenon in the entire story of cosmic evolution. In the end, maybe that's the real story worth celebrating and marveling at. Not just whether time had a definite beginning, but that we're the kind of beings who can ask that question and actually have a reasonable hope of finding an answer. The universe somehow gave rise to conscious observers capable of understanding, at least partially, where they came from and how they got here. Atoms and particles, governed by impersonal physical laws, arrange themselves over billions of years in just the right configuration to become beings that can contemplate their own origins and the origins of everything that exists. And as we continue pushing forward into the unknown, developing better theories, conducting more precise observations, building more sophisticated mathematical tools, and thinking more deeply and carefully about what our equations really tell us about reality, we're extending the frontier of human knowledge into territory that previous generations could barely imagine. We're exploring questions that our ancestors thought would forever remain the exclusive domain of philosophy, theology, or pure speculation. Whether we ultimately determine that time had a definite beginning or discover that it extends infinitely into an unknowable past, the journey of discovery itself is absolutely worth celebrating. The tools we've developed, the understanding we've gained, the questions we've learned to ask precisely, and the methods we've created for addressing them represent some of the highest and most impressive achievements of human civilization. They show what's possible when curiosity, creativity, mathematical reasoning, and careful observation are combined and directed toward the deepest mysteries of existence. So the next time you look up at the night sky on a clear evening, remember that you're not just seeing distant points of light scattered randomly across the darkness. You're seeing evidence of cosmic history stretching back nearly 14 billion years. Those photons entering your eyes began their journeys in ancient stars, some of which no longer exist, carrying information about the chemical composition and physical evolution of the universe. And somewhere in that vast expanse of space and time, encoded in subtle patterns of cosmic expansion and tiny fluctuations in the cosmic microwave background radiation, embedded in the mathematical structure of general relativity and quantum mechanics, may lie the answer to one of humanity's oldest and most profound questions. Did everything have a beginning? Or does time stretch infinitely backward into an eternal past that has no starting point? We don't know the complete answer yet, but the remarkable thing, the truly extraordinary thing, is that we're closer than ever to finding out. And that journey of discovery, that human quest to understand our ultimate origins, continues to push forward, one observation, one calculation, one insight at a time, bringing us ever closer to finally knowing whether the universe began with the Big Bang, or whether something even more mysterious and wonderful lies beyond that apparent boundary at the dawn of time.